Okay, so we've completed the chapter on kinematics, we've completed the chapter on forces and Newton's laws, we've completed the chapter on work, and using the concept of work, in our last discussion lab, we introduced the concept of conservation of energy. And so to demonstrate all of these different methods that we now have to solve problems, we're going to solve this problem, which we've solved before, but now we can solve it 3 different ways. So let's go ahead and read the problem. Throw a ball straight up from the top of a building. What is the speed of the ball just before it hits the ground 55 meters below? Okay, so this is a kind of classic type problem that we can figure out using multiple concepts in physics. And so let's go ahead and first do what we always do and define a coordinate system and write down our knowns. Alright, so they told us in the problem that the initial speed of the ball, or they told us at least in the diagram here, the initial speed of the ball is 14 meters per second, and they told us that the ball is 55 meters above the ground. So that means that the magnitude of the displacement of the ball in the y direction is equal to 55 meters. In order to define more of our knowns, we need to define a coordinate system, right? Because things like velocity and acceleration are vectors, so we need to define a coordinate system in order to do that. And so I'm going to choose my origin to be kind of the ground right below, all the way down below the ball. And that makes the plus y direction straight up. And of course the plus x direction is to the right. But I've drawn this diagram a little bit funny. The ball is being thrown straight up, so in reality the ball is going to travel straight up in the air and then fall straight down, so it's going to be entirely motion along the y direction. I did draw it with a little motion in the x direction just so you can kind of see it going up and coming back down, but really this is a one-dimensional problem, right? The only motion is in the y direction. So now that I've defined my coordinate system, I can write down more knowns, right? I can now say that my initial velocity is equal to 14 meters per second j hat, right? It's positive velocity in the plus y direction. I can say that the initial height of the ball, or the initial position in y of the ball, is equal to 55 meters. And that means that when it hits the ground, the final position of the ball in y is just equal to 0, because we've defined that to be our origin, right? When the ball hits the ground, that is y equals 0. And then of course we have one extra known that we can bring into this problem from our kind of conceptual knowledge, and that is that the acceleration in the y direction is equal to negative g j hat, right? It's going to have acceleration in the minus y direction. It's going to be a constant acceleration given by g, the acceleration due to gravity near the surface of the Earth. And so we have all these knowns, and we previously would have solved this problem in for example, using force and kinematics, but let's go ahead and start with our newest method, which is the method of conservation of energy. And so let me just write that down. So again, we have 3 methods to solve this problem now. And so my first method I'm going to try is conservation of energy. How do I know I can use this method? Well, I guess I didn't write it down explicitly when I wrote down the problem, but typically with this type of problem, we're going to assume that there's no friction or no air resistance. If that's the case, if there's no friction, no air resistance, and the only force affecting this ball as it flies through the air is a force of gravity, then gravity is a conservative force. There's no non-conservative forces like friction, and so the total energy of the ball should be a constant, right? That's what conservation of energy means. And so we go ahead and write down our equation for conservation of energy. It's really simple. E1 is equal to E2. All right, this means the total energy of the ball at time 1 is equal to the total energy of the ball at time 2. I could pick any time 1, any time 2, and the total energy of the ball is just equal to some constant, right? This is just equal to some constant. At all moments in time, if I sum up all the energies that this ball has, it'll add up to one constant number. And so it's up to us to figure out what is E1 and what is E2. Well, in general, your total energy is going to be a combination of potential and kinetic energies. And so we could in general write that at time 1, when we're throwing the ball, right after it leaves our hand, we have some gravitational potential energy. I'll call that U1 for the gravitational potential energy at time 1. And I have some kinetic energy. At time 2, I may also have some gravitational potential energy and some kinetic energy. These may be different, right? The ball has traveled through the air, it may have sped up, it may have lost potential energy, but no matter what, these two, the sum of the potential plus the kinetic has to add up to some constant. Okay, I have equations for potential energy. I know that the gravitational potential energy is equal to mgy1, right? It's based on what is the value in the y direction of its position at its initial time. What about kinetic energy? Well, we throw it some initial velocity, and so it has some initial kinetic energy. Okay, so that's good. What about at time 2? Well, at the moment, time 2 is some arbitrary time, so let's just write in general that the gravitational potential energy at time 2 is mgy2, and the kinetic energy at time 2 is 1/2 mv2 squared. Okay, and now let's go ahead and pick our two times. Let's pick time 1 to be the moment the ball leaves our hand, and so we definitely have gravitational potential energy at that time because the ball's leaving your hand at a height of 55 meters, and we definitely have kinetic energy at the moment because it's leaving your hand with a velocity of 14 meters per second. At time 2, let's pick when it hits the ground. Okay, let me label that here. I'll label this time 1, this time 2. So when it hits the ground, well, y2 is equal to 0. So that term just goes away. There's no gravitational potential energy when it hits the ground. It will have kinetic energy when it hits the ground, right? So we'll leave that term as is. And so what we're telling here is that whatever potential plus kinetic energy we started with will all be kinetic when the ball hits the ground. I can also note that the problem didn't tell us about mass, but I can now see that mass is just going to cancel out, right? All my mass terms will just divide out. And so it doesn't matter that we don't know the mass of the ball. That's okay. And so our unknown is v2. What is the velocity of the ball when it hits the ground? So I can go ahead at this point and just solve for that, right? v2 is equal to the square root of 2gy1 plus v1 squared. Okay, that's just simplifying that equation that we just wrote down for v2, and I know everything in this formula now. I can go ahead and plug in. This is equal to the square root of 2 times g, which is 9.81 meters per second squared, times y1, which we know is 55 meters. We already wrote that down. And then minus v1 squared, which is plus 14 meters per second squared. And so plugging this all in, we find that the final velocity of the ball when it hits the ground is equal to 36 meters per second. Okay, so we got an answer using conservation of energy, and it was relatively simple to find that. Okay, we found the velocity of the ball when it hits the ground. Okay, so that's method 1, conservation of energy. What about method 2? Well, I'll go over here. Let's try method 2. Method 2 is let's use the concept of total work and the relationship between total work and kinetic energy. Right, we learned in the previous chapter that work and kinetic energy are related. And so our goal here is to use the work energy theorem to solve for the final velocity. But let's first figure out what is the work done by gravity as this ball falls from the top of the building to the ground. Right? Our equation for work in general is going to be the integral of f dot dr. Okay, it's our line integral where we take the dot product of our force and our infinitesimal displacement dr. But in one dimension, as we're only moving in the y. This simplifies into the y component of our force, dy, and the y component of our force is a constant, so this simplifies even more to fy times the displacement in y. Alright, so that's not so bad. So if I want to figure out the work done by gravity as this ball falls, well, I just have to plug in what is the force of gravity. I can, of course, draw a free body diagram for that. I draw a dot to represent the ball. I have the force of gravity pointing down, right? We defined that direction already to be the minus y direction because we defined up to be plus y. So the force of gravity is just the force of gravity down, and we know that to be equal to mg. So the force of gravity here in the minus y direction is minus mg. Okay, and our displacement in y is just y2 minus y1. And we defined the ground to be equal to 0 position y, which is y2, right? That's our final position of the ball. So that just goes to 0. And so the work done by gravity as this object falls is just equal to mg times the initial height y1, right? So it doesn't really matter if the ball is going way up into the air and coming back down. All that matters is the displacement in the y direction of 55 meters multiplied by the force, okay? And that's the work done by gravity. We can note here that since the force of gravity is the only force, that tells us that the total work done on this ball is equal to just the work done by the force of gravity. And so now we can go ahead and use our work energy theorem. Okay, our work energy theorem is that the total work done on an object is equal to the change in the kinetic energy of the object. Or that's equal to 1/2 the mass times the velocity of the object at time 2 squared minus 1/2 the mass times the velocity of the object at time 1 squared. Okay, that's what our definition of changing kinetic energy is. And so now that we have that, we can just solve this for V2, right? This means that V2, that's what we want to know, what is the velocity of the ball when it hits the ground? It's going to be equal to the square root of 2 times the total work divided by the mass plus mass times the initial velocity squared divided by the mass. Okay, I'm skipping a little bit of mathematical steps there, but not too many, so I hope you can follow along. And we can plug in here, well, we can first note that this mass term cancels, and I can plug in our equation that we found for the work done on this ball by the only force acting on it, the force of gravity. So I plug that in. V2 is equal to the square root of 2 times mgy1 all divided by m plus v1 squared, and our mass cancels there. And so that's good because we don't know the mass of the ball. We're glad it's canceled. And we end up getting this formula, square root of 2gy1 plus v1 squared, which we know is exactly the same formula that we had found already using conservation of energy. So that's good. We can go ahead and plug in, and we find our velocity of the ball when it hits the ground is equal to 36 meters per second. Okay, we get the same answer. So that's really a good check. So those are our first 2 methods to solve this problem. The first was using conservation of energy. The second method was using total work. The third method is what we would have done a few chapters ago. The third method to solve this problem is noting that we can use Newton's laws to figure out the acceleration, and then we can use the fact that it's constant acceleration. We can use kinematics to solve for our answer. Okay, so once again, we have our free body diagram over here on the left, and right from that free body diagram, we can plug into the sum of the forces in y is equal to the mass times the acceleration of the object in y. I only have one force acting on the ball in the y direction. That's equal to minus mg. That's equal to mass times acceleration of the ball. My mass cancels, and I end up getting that the acceleration of the ball is equal to minus g. I can note that this is constant, which is a good thing because we have equations that apply only when the acceleration is constant. These are our constant acceleration kinematic equations. The one that will be most relevant to us here is this equation. V squared is equal to v naught squared plus 2a delta y. Or instead of using v naught for the velocity at time equals 0 and v for being the velocity at some later time, maybe I'll just rewrite this in terms of the notation we've been using, which is v2 squared is equal to v1 squared plus 2a delta y. Right, where v1 is a velocity at time 1, v2 is a velocity at time 2. And now we can go ahead and plug in. Right, this is equal to v1 squared plus 2. We know the acceleration is equal to minus g. We already found that. And delta y is just equal to y2 minus y1. We know that y2 is just equal to 0 because we define the origin to be the ground, which is the final height of the ball. And so this will simplify to become v1 squared plus 2gy1. And so that means that the final velocity of the ball is equal to the square root of, just rewriting this in a little bit different order, 2gy1 plus v1 squared, which again is exactly the same equation we derived using method 1 and method 2. And so we can now plug in and find that the velocity of the ball is equal to 36 meters per second. Okay. So we have 3 different tools in our toolbox that we can now use to solve this problem: conservation of energy, total work, and kinematics. Okay, a lot of the time this problem is going to be easier using conservation of energy because it just handles a whole range of situations in a much easier way. Right? We don't have to use any vectors. It's just a scalar calculation, and we can solve very quickly. And let me just reflect on that a little bit more. So let me use this corner here a little to reflect. The nice thing about conservation of energy is that if I had given you this problem, I'll just redraw my building here, and I have some windows on that building, and I could have thrown the ball straight up like we just solved for, or I could have thrown it straight out, or I could have thrown it straight down, or I could have thrown it at some angle. I could call these 3 situations A, B, C, and D. The thing about the conservation of energy method is no matter which of these options we're choosing, A, B, C, or D, we're going to get the same answer very quickly, right? Because look at our equation for conservation of energy. The initial potential energy is not changing. It's still based just on the initial height of the ball. The initial kinetic energy is not changing because it only depends on how fast we're throwing the ball, not on the direction we're throwing the ball. The final height of the ball is still 0. It's going to hit the ground, and we can very quickly figure out what is the final velocity of the ball. So with conservation of energy, we don't have to deal with vectors at all. We can tell that with A, B, C, and D, that the velocity of the ball when it hits the ground is going to be 36 meters per second. Right? That's for each of these cases. Doesn't matter which direction we throw the ball, straight up, straight down. When it hits the ground at time 2, it must be moving at 36 meters per second. Right? If we have done that using method 3, it would have been a lot of work for us to do, for example, B or C. Right? We would have had to solve this problem in the x direction and the y direction. We would have had to figure out the x component and the y component of the ball's velocity when it hits the ground. We would have had to do some trig. It would have been a little bit of work. With energy, we can solve that really quickly. Other reflection is that the type of problems that become much easier with with conservation of energy, typically are asking about velocities, right? This question was trying to ask, what is the velocity of the ball when it hits the ground? Well, since kinetic energy depends on velocity, often energy is going to be the easiest way to solve an energy problem. If the problem had asked how long is the ball in the air for, most likely method 3 would have been easier for that, because energy doesn't tell us anything about time. So this is our first kind of summary of these 3 different methods, and we're going to get a lot of practice on this in the next few example problems.